Hi, everyone. There were two problems we did not get to, two sample problems I wanted to do with you before you go try some accelerated motion problems on your own. And so we just did two of them with an aircraft, its rate of acceleration, and also its displacement, or how far it went down the runway during takeoff. Uh, here's a here's a type of accelerated motion we touched on briefly today out at the bridge. We dropped a couple weights, and we saw that they fell together at the same rate. So assuming there's no air friction, which is what we're going to do for all these problems, any dropped object, any free fall problem, we'll assume that air friction plays a negligible role. And so let's go ahead and solve this one here. If a rock is dropped off a high cliff and hits the ground 4 seconds later, how high is the cliff? Well, let's be let's have a good approach here by listing our givens and wanteds. And since it's free fall, we know that acceleration is g, is -10 downwards, 10 meters a second faster every second, right? Whatever it is that got dropped. It's going about 22 miles an hour faster every second downward. It is going about 10 meters a second faster every second downward. And it hits the ground 4 seconds later, so t is 4.0 seconds. And what is not really explicitly stated here, but should be knowable, is knowable indeed. If it's dropped out of your hand, it had a starting velocity of 0. V initial is 0 meters a second. And what do I want? How high is the cliff? So really what I want is displacement. I'm going to call it y-axis displacement. And you'll see why when we get to projectiles. But I'm looking for displacement. So in fact, let's do this. Let's write down the equation as I've written, which is x is v initial t plus 1/2 a times t squared, because I've got time, I've got acceleration, and v initial is 0. It was in my hand to begin with. But instead of saying it's an x-axis displacement, let's just call it y-axis. We didn't change anything. We're just thinking forward a little bit, knowing that these rocks are falling downward on the y-axis. So let's just say y equals 1/2 at squared. Okay, so how high is the cliff? Well, that's sort of like how far did the rock drop? It's not sort of like it, it's exactly like it. So y equals 1/2 of -10 meters a second faster every second. T squared is 4 seconds squared. Okay, so well, that's going to be -80, right? So 1/2 of -10 is -5, and -5 times +16 is 80. So let's see here. So y equals, and it's a -80. What does that mean? Meters. Well, that means the displacement was on a standard coordinate system. The displacement was that way in the negative direction. So it fell from 0 meters down to -80 meters on the y-axis. That's what just happened there. Okay. So how high is the cliff? 80 meters if you fall for 4 seconds. Okay. And the next one, I'm just going to leave this running. I'm going to close that down. Looks like I've got to do this one here. Okay, so similar question, but now we're looking for time. How long would it take King Kong to fall from the top of the Empire State Building to the ground below? A distance of 380 meters. Well, good practices have us making lists, even when we think we could pull it off quickly. Let's go given wanted. Acceleration is -10 meters a second faster every second. That's known because he'll be in free fall when he falls. All right, and a distance of 380 meters. So he falls. I'm going to go ahead and say his y-axis displacement is -380 meters. I'm going to call where he starts 0. Right, so here's the building. There's the building, and I'm going to call this position on the y-axis 0, and I'm going to call this position down here 0 meters, and that's going to -380 meters. He falls downward from 0. Starting point is at 0. Falls down to the ground below to Fifth Avenue, well below. Let's see, what else do we know here? Well, nothing else is stated explicitly. But again, if he's hanging onto the building before he falls, then his initial velocity, he's falling from rest. So 0 meters a second, and we're looking for t, time. How long does it take? So you go to your list of equations, and the first equation you see that has time in it is delta v over delta over t, but that's not going to help because we don't know his change in velocity, right? And then, of course, when you write this as what's the difference? What's the difference in velocity? The change in velocity is final state minus initial state over t. Multiply both sides by t, and add that v initial over, and you get the first kinematic equation, which is v initial plus at. Right? Is that going to help us with how long? It's not, because while we have v naught as 0, we don't know his final velocity. So this one's not going to help us. That's no good. We go to the next equation, and it says x equals, I'm going to write y equals, since he's falling downward. If you just want to leave it as x, it doesn't matter. Just know that we're talking about vertical motion here. Y equals v initial t plus 1/2 a times t squared. And again, we're in the special case where he starts from rest. So his distance that he falls is equal to 1/2 the acceleration times the time squared. Well, look at this. We've got the distance and we've got the acceleration. So let's solve for time. And let's do it algebraically first. Well, that weird thing, it's a 1 over a 2. That weird thing confuses me. Therefore, I'm going to get rid of it. How do I get rid of a 1/2? I multiply by 2. And if I do it to one side, I must do it to the other side. So then I get, multiply both sides by 2, I get 2y is at squared. I'm solving for time. So I'm going to divide by a. So t squared is 2y over the acceleration. I don't want t squared. I just want how long. So I take the square root of both sides. And so t, oops, that's supposed to be t, sorry. T will be root of 2y over acceleration, both of which we have. How long does it take King Kong to fall? The square root of twice y, so twice times negative 380 meters over the acceleration of negative 10 meters a second faster every second. And eyeballing that, I don't know. It's like in the 8 to 10 second range, because we're at like nearly 800 over 10. We're somewhere in the realm of root 80. Yes, we're in the realm of 8 to 10 seconds. But let's run the numbers. All right, let's run the numbers here. Square root of 2 times 380 over 10. Close them out. Notice I dropped my negative signs because I've got one here and I've got one here. I essentially, in my mind, I just multiplied everything by -1, just to, if you got negative above negative, it's going to be positive. So that's why I dropped them, and I get 8.72 seconds. So he's going to fall for 8.7 seconds or so before impacting Fifth Avenue below. All right, so I just wanted to do those two problems for you. Roger Dodger, over and out. I hope to see you on Tuesday, tomorrow, and if not, we'll catch up on Wednesday.